This is going to be a fun lecture for me because we've been working on this for years now, and I've never had a chance to talk about it in public before. So a lot of the things that you're going to be hearing, you'll be hearing for the first time that it's been talked about outside of non-disclosure presentations or outside of thinking machines. I may screw up on presenting it because I haven't had much practice presenting it, and so I hope bear with me. What I'm going to be talking about is the new architecture that Thinking Machines has just introduced called the Connection Machine 5. And I'm going to approach it by talking a little bit about the history of the previous machines and what we learned from them, and that will motivate something of what the architecture is. So the beginning part will be sort of general architecture talk. And then the second part will be a discussion, since you're computer scientists and electrical engineers here, about a lot of the implementation details we got into once we had decided about the architecture, and just sort of the puzzles we solved and how we solved them. And if there's a time at the end, maybe I'll summarize a few points about what I think is important about this architecture in terms of where it points us to the future. So I'm going to start by describing the motivation of the very first connection machines, which started really almost 8 or 9 years ago when I was at the Artificial Intelligence Laboratory. And I got very interested in building thinking machines, I guess you would call them, machines that reasoned. And at the time I was mostly working on robotics. So I went to Marvin Minsky and I said, you know, I think I'm going to build a parallel computer. And Minsky said, well, that's a good idea as long as you don't make the same mistake as they made in the ILLIAC 4 and have it run only one program. And so I thought about that for a while, and I went off and I actually built a little machine that was a bunch of Z80s talking to each other, and discovered that I couldn't program the thing. I couldn't get them to all work together. They were always stepping on each other's toes. And at that time, there was someone who was a graduate student in the AI lab named Scott Fahlman, who was working also on common sense reasoning. And he had a very specific program in mind and a sort of machine that he imagined to run it, which was his Nettle machine. And the great thing about Scott Fahlman's machine was because it ran a single program, basically what it did is it mostly ran a sequential set of steps, but each step did tens of thousands of things at once. So you had a sequential program flow, but you still had a lot of parallelism. So I started looking at that and I said, gosh, what he's doing is an awful lot easier than what I'm doing because he's actually got a program for it to start with. So I went back to Marvin Minsky and said, I've decided to make the ILLIAC 4 mistake, and I'm going to build a machine that only runs one program. So it basically started. The whole thing was sort of an interplay between software ideas and hardware ideas. And that idea of running only one program, because that was all that I was smart enough to write, was sort of the central software idea that we started with. And I actually started designing at MIT and then ended up building at Thinking Machines the first version of the connection machine, which was based on that one program idea. So this was the CM1. And the idea was that you had an ordinary computer, which is what ran the program. So this is called the host computer. And that computer could talk through a broadcast network or a control network to a zillion little bitty simple processors. So in the CM1, they were single-bit processors. They were tiny processors, each of which had its own little 4 kilobit memory. So this is a processor and a memory, and so on. And what you could do is when you got to a step that said, for example, increment all 64,000 numbers, this could send down an instruction to all of them and tell them all to increment. So they were all following the instructions up here. This is a classical single instruction multiple data machine. When the processors needed to talk to each other, there was another network called the data network which in that machine was based on a hypercube, that acted like a kind of telephone switching system that allowed all of these to send messages to each other. So the basic operations were everybody do the same operation like an arithmetic operation or a Boolean operation, and also everyone send a message. They also had the ability to locally decide whether or not to obey an instruction based on conditionals within the memory. So that basic programming model of sort of one program with almost this accelerator on the back of it was the way that the first connection machine was built. Now, as soon as we started actually using that machine, we began to change the program model. The particular way that we started changing it first was something called virtual processors, because we began to realize that there was nothing magic about 64,000, and it was kind of inconvenient to force your problem into being exactly 64,000 elements and talking about 64,000 things at once. So we began to develop a new programming model from our experience on this machine, which was virtual processors. And the idea there was that you had an imaginary machine that had effectively an infinite number of processors. In fact, it had as many as you had data elements. And that somehow some combination of the hardware and software was to simulate that machine on this machine. So each of these machines had to do the job of a whole bunch of different virtual processors. So for instance, if you had 1,000,000 virtual processors, you could do it on the 64,000 processor machine, but each processor would do the job of 16, and it would take 16 times as many steps. The other thing that we began to see was important is some particular patterns of communication. So not just the communication of broadcasting out and doing point-to-point communication, but there was another graduate student then around the AI lab who used to come to thinking machines by the name of Guy Blalock, who started using these primitives called scans. And so realized that that was also a very important part. And we began to build up a set of programming primitives, which in some sense were a little bit abstracted away from the machine, but still had this notion of one program going on at once. So once we actually started running virtual processors on this machine, we started discovering a lot of flaws with the hardware. Now, flaw number one was we just plain didn't have enough memory. In the CM1, these were 4 kilobits each, so half a kilobyte of memory on each processor. There's 32 megabytes across the whole thing. So as soon as people started having millions of virtual processors, you quickly ran out of that, and it was a huge limitation. The other thing that happened was sort of a practical thing. It turns out the AI people didn't have any money to buy these machines. We sold about 2 of them to AI people. And the people that really wanted to buy them were the physicists. People who were doing things like simulating airplanes and fluid flow and interactions of particles and things like that. And they were all interested in doing everything with floating point numbers. The other thing that we ran into is that while we sped up all this computation, the thing became completely dominated by input-output. So we hadn't sped up the input-output, and we were only speeding up the core part of the computation. So the input-output was half the problem, so we only sped it up by a factor of 2. So the next step was the CM2, and it began to fix some of these problems. So first of all, we added a lot more memory. And we put basically 256 kilobits of DRAM on each one initially. The other thing that we did is we put a group of processors together. You see, we were doing floating point by these simple bit serial processors. And it took a long time to do floating point in the very simple processors we had. So what we did is we added floating point units, but the floating point units really worked with a whole cluster of processors. So in a sense, we built a bigger processor by clustering together a group of 32 little processors. So we put a floating point processor with each of those. So in a sense, for some purposes, you could treat these all as one processor, doing floating point operations, or for doing something like indirect addressing into the memory. And you can treat them as bit serial processors. Now, if that seems to you like it's kind of a kludge, you're right. But it was necessary because we had built up a set of software which required the bit serial processors, and in fact, they were very useful for a lot of things. And this concept of virtual processor let us hide all that detail. So since the compiler was really compiling things in terms of virtual processors anyway, people didn't really have to know whether they were dealing with 64,000 little bit processors or 2,000 big floating point processors, because that was just different numbers of virtual, they were all virtual, they were describing things in terms of virtual processors anyway. So in fact, this clustering of the processors for the purpose of doing things like floating point arithmetic and indirect addressing within the memory was completely invisible to the users. The other thing that we did was we actually connected I/O into the processors so that you could do parallel I/O into a lot of processors at once. And we built I/O devices to keep up with that. First, just a frame buffer, and then a disk device, which consisted of 40 disk drives that ran in parallel so that you could write a 32-bit word on 32 drives, 1 bit on each drive, and the error correction code on the rest of the drive so that if you had a drive crash, everything could keep on going. That's what's these days called a RAID system. And that became our data vault disk. The other thing that we did was multiple users wanted to use these things at once. So we put in the capability of having so that you could partition up the machine
and use, say, half of the machine for one user and half of it for another, or sometime maybe at night you could use the whole machine. Use the whole machine at once. So that was the machine's main product. Started using the T word, talking about teraflops of computing.
And at the time, that seemed almost an absurd concept because we were very proud at that point that we could actually get gigaflops out of this. So that was hundreds of times faster than what we were getting at the time. So we decided that the architecture from the very beginning, we should design the teraflop version of it. And then it would be very easy to build smaller versions of it until people could afford the teraflop version. But then we should really take the teraflop seriously from the start. So goal number one is teraflops, and a flop is of course a floating point operation per second, and a tera is a million, sort of the next one up after kilo mega, giga, tera. So a teraflop of real performance, which meant that we had to actually have greater than a teraflop of peak performance, probably a couple of teraflops up to, depending on the problem, 2 or 3 teraflops of peak performance to really get a teraflop. So that meant that we had to talk about terabytes of memory. We weren't going to make the memory mistake again. No. That would be amazing, a terabyte per second. If only our users would expand their memory at such rates. So terabytes of dynamic memory. And of course, terabits per second of I/O to and so on. The other thing that I guess was a consequence of these goals was we realized if we were really going to build a machine that big, it was going to have in it some kind of fault tolerance, because there was no way that we could get that much hardware to work for more than a day at a time. And this machine was going to cost a lot of money, and people would complain if it broke every day. So that was another sort of central driving notion in the whole thing, was that we had to have high availability. And of course, we had to have things like time sharing, forward compatibility with the CM2 software. And it turned out that a side effect of this architecture is we also picked up a lot of other kinds of software too, because of course you can use this as a memory machine if you sort of ignore this part of it. And so in fact, we could run any code that anybody had written for a purely memory machine too. So those were the goals, that sort of flexibility of programming style, this kind of performance range, and the consequence of that was fault tolerance. So I'm going to go through some of the decisions we made fairly quickly. What time has it? Okay, good. Okay, so first, the processing node. There have been tremendous progress in the development of RISC microprocessors from the time we did the CM1. And they're great deals because there's a whole lot of engineering going into them, and you would like to be able to capitalize on that engineering. So we knew we wanted to use a standard RISC processor. It turned out that there was no RISC processor that gave us nearly the cost performance that we wanted on parallel things, because it turns out that the kinds of algorithms that you run on a parallel machine are a little bit different than the kinds of algorithms that you run on a workstation, and the RISC processors were really optimized for workstations. So what we decided to do was to use a standard RISC processor as a core, and then add to it the special things that we needed to do very well in parallel. So the RISC processor that we chose initially as a core was the Spark processor, primarily because it just had the largest existing software base, and we wanted to capitalize on that. So the basic central thing was a standard off-the-shelf Spark processor. And 32 megabytes of memory. And of course, we had to add to that the ability to talk to these two networks. And so we added a special chip to that, which was the network interface. Now, what's wrong with the picture? What's wrong with the picture was we didn't have nearly the memory bandwidth to keep up with the parallel computation that we wanted to. But we really wanted to get something. These parallel algorithms did a lot of, because of the virtual processors, tended to go through memory and touch all locations in memory or a lot of locations in memory. And so the cache in the Spark processor wasn't big enough to hold the locations, and we just felt caching wouldn't really work. So normally in a workstation, you can kind of depend on the idea that you have kind of a working set that you hold in cache, and so you're not too limited by this memory bandwidth. With a parallel processor, since you're actually processing all the data, and that's the whole idea of data parallel, you really touch all the stuff, cache just doesn't work that well. So we put a way around that memory thing And we put a set of processing units, which you can think of as vector units on here, which each had its own 64-bit paths to memory. So that we had a bandwidth going to memory here of 0.5 gigabyte per second. This is in one node. And these were vector, let me call them vector processors, that can go through memory and touch all the memory directly, that work, that there's not an intervening cache. So that the Spark processor, when it formulated an instruction and said, okay, we want to go through and add all of these locations to all of those, it actually puts that instruction to the vector processor, which has much higher bandwidth directly to memory. This is not, I think, critical, because the whole system is sort of designed with the assumption that what's inside the processor is going to upgrade over time. And I think the people that are designing RISC processors are beginning to understand that this bandwidth to memory is a real problem. So maybe that someday we'll be able to just use a standard RISC processor. But right now, this is what we mean by a processing unit. And this part of it is optional. So that's the processors. And the sort of critical specs, the peak instruction rate is 128 megaflops per second. And that will be doing something like a multiply accumulate as you do in a dot product. And 32 megabytes of memory, I've got that. Now, the next elements were the networks. In order to have the processor really be scalable up to a teraflop, we realized that we had to have a network structure where the bandwidth of the network was scaled uniformly. We looked at problems, real problems that people were doing, because remember by this time we've got a lot of users out there running on CM2s. It turns out that the bandwidth that they require of the network actually scales with the number of processors. So if they have twice as many processors, they really want twice as much bandwidth out of the network. So that completely eliminates using something like a two-dimensional grid, because in a two-dimensional grid, when you make it twice as big, the number of wires going across the center of it doesn't go up by a factor of 2. It only goes up by a factor of the square root of 2. So we needed a network that built up like that. And of course, we wanted a logarithmic network, too, because we wanted to minimize the latency across it. Although, let me say the bandwidth was more a driving factor. So what we ended up doing was using a kind of a butterfly structured network that came out of some ideas of another CMU person, Charles Weiserson, which, when you added more processors, added more layers. So it was one of these kinds of things. It's a little bit more complicated than that. But the idea was that when you added another set of processors on here, like this, you would actually add another layer of wires up on the network. So you'd actually plug in more switches to go across, so that the latency of the network, the number of wires you would go through, would go as the log. So the cost of the hardware would grow in terms of wires more than in proportion, although wires are pretty cheap. So most of your cost is still in the processors. But the bandwidth across it would grow in proportion. So the number of wires that cut across the center, whatever the center was, would be proportional to the number of processors in the machine. And that basic method was used in both networks of the machine. Now the other thing that we did in these networks is we used an adaptive routing algorithm that we had been very successful using adaptive routing algorithms in CM2. That is, the path that a message took going from one processor to another was dependent on the other messages in the network. So if there was too much traffic in one side, it would take a side route. This had great benefit when we start talking about fault tolerance. But the point was that there wasn't just one way of getting from one processor to another. There were a lot of alternate paths, and messages could pick a free path in the network when another path was blocked. That was another critical feature of it. Of course, also we used the same technique of wormhole routing that we used in the CM1 and the CM2, where rather than packet switching it by stage, you actually sort of pipeline the packet through the network so that in some cases, so you were actually switching as soon as you looked at those first bits coming along, so that you could actually be delivering one end of the packet while the beginning of it was still being transmitted, rather than a completely stored forward thing. That was also very important for minimum latency. So those were the key characteristics of the networks. The two networks are a little bit different in detail, but they're both kind of that idea. Now, that sort of brings us to the notion of fault tolerance in the machine. What we wanted was a way that you could continue running the machine when a piece of it was broken. So that involved a bunch of things. First of all, the hardest thing, it turns out, is noticing that a piece is broken. So there's a whole other network in this machine, which I didn't draw, which sort of encompasses the whole thing, completely independent network called the diagnostic network, which can talk to all of the chips in the machine and notice when something's wrong, run a complete set of test vectors on that chip, isolate that chip out from the network, and so on. In fact, we can run as thorough diagnostics on each of the chips as we can run them in the chip tester. In fact, in point of fact, we run more thorough diagnostics in the machine than we do in the chip tester. So that was important to be able to get at the information. The other point is to do an awful lot of error logging along the way. So for example, just to sort of show you the extremes we went through, when you send a message from here to here, you don't just check it at you don't just add a check code and see if it's corrupted when you get there, but you actually check the check code at each step along the way. So that if you ever lose a bit, you can tell exactly what wire you lost that bit on. You know exactly what to suspect. It narrows it down to 2 chips immediately. 2 chips and 1 wire. The one that sent the message and the one that received the message. The diagnostic network can then go in there and can look at it and actually do testing on the wire. It can send, for instance, a signal down the wire and measure it with enough degree to tell if the terminator resistor is out of there or something like that. So there's a lot of test hardware built into this. There's even, for example, one thing you might worry about is a message gets transmitted but nothing ever receives it, so nothing ever checks it. So there's actually hardware in there that keeps track of every single message that gets transmitted and keeps a scorecard, make sure everyone gets received. So you can actually go and find out where it got dropped if it got dropped. That's a lot of hardware. In fact, probably about 40% of the hardware in the networks is somehow to do with error checking or recover or something like that. And it sounds like overkill. All of these seem like really rare events. But when you have a huge amount of hardware like you will in a teraflop machine, you've really, all these unusual things actually happen. We've got stuff like the error correcting codes, for example. You can't use a standard error correcting code in the memory here because there's a failure mode of the chip. If you use a 4-bit wide chip where all 4 bits in the chip fail at once. And so it's not just the 4th power of the error rate, there's this sort of non-independent failure mode. So you have to use a special error correcting code that notices that kind of failure. So there's a lot of attention to detail like that to notice when errors happen. Well, then what happens if an error happens? Well, of course, you've lost the computation unless you've checkpointed it. So we have very elaborate checkpointing facilities in the machine that either checkpoint at regular intervals or checkpoint on program control to the mass storage system, the state of your computation. So what you can do, if you find an error, you find the part of the machine that has failed. It might be a processor, or it might be a switch in the network, or it might be that you can narrow it down to some group of things and you're not exactly sure what. And you actually, through the diagnostic network, electrically slice out that part of the machine. You tell all of these processors don't talk to that one. And you remap the machine into a spare set of processors. So each of these processors has to have in it actually a little kind of a page map that tells you where the good processors are so that you can keep that image of a totally contiguous address space, even though, in fact, you've got holes in it because you've switched in a spare processor or something like that. So all that is in there and actually works. It turns out to help you a lot with things like time sharing too, because a lot of the protection mechanisms that you have to put in for this are protection mechanisms that help you with time sharing when you're trying to keep one user from hurting another user. Okay, and in fact, a very specific example, for instance, is the ability to pull everything out of the network quickly to look at the state. You actually use in time sharing. So if you're running a time sharing job, you can actually when you swap from one user to another user, you can actually pull all of these messages that are flying around the network out, put them away, bring in the next user, and then throw them back into the network when the user gets sliced in to the next time slice. So a lot of the mechanisms for time sharing and fault tolerance are shared. There are also some packaging things about fault tolerance, which maybe I'll get to in packaging. Actually, I can just say the simple idea is you have to be able to power down part of the machine so that if there's failed components in it, you can fix that part of the machine offline while the rest of the machine continues to operate. Let me talk a little bit about clocking. These machines are physically very large. The largest machines that we've sold so far are 1,000 processor versions, and the 1,000 processor version is kind of from here to the wall in terms of a rack of cabinets. And for a teraflop, you need a 16,000 processor version. So it would fill up a good chunk of this room. So physically, they're much larger, even in the 1,000 processor version, than the clock period of the machine. But in order to keep this programming model really working right, absolutely reliably, we felt we had to have a synchronous machine. That is, we had to have a single clock in the machine that everything is marching to the beat of the same drum, that things are absolutely deterministic. If you run the program, it will do exactly the same thing the next time you run it. So the way that we accomplish that is we very carefully distribute the clocks over measured wire and have local phase lock loops throughout the machine. And every network chip, for example, has built on it a phase lock delay element that locks its local clock into the system clock of the whole machine. So they're sort of always synchronizing off each other's watches so that the whole system clocks together. One part of it can't. Now there may be phase lags, but you'll never have one part get an extra cycle in there from the other parts. Then once you've got the thing synchronous, you can have wires that go across the machine that can be longer than a clock period, as long as they're either about 1 clock period or about 2 clock periods or about 3 clock periods. Then the system will always deterministically know that, hey, this wire gives me a delay of 3. So there are bits flying around the machine that are not stored in memory but are actually stored on a wire. So you're actually putting a couple of bits in a wire before you get one out. So there's a lot of careful electrical work to make sure that that really works. And it does really work incredibly reliably, actually. I mean, you do everything with differential signaling, and you use very conservative timing to make sure if you didn't cut the wire quite right, it doesn't matter. You don't shift to the next phase, and so on. So that was a tricky part of the machine. Other thing, I'll just say just a tiny bit about packaging. Basically what we do is we take these nodes, we put 4 of them onto a board with the appropriate memory. And the board is actually kind of 3-dimensional structure. There's a board of processors, a board with the memory on it. They're sort of sandwiched together, and then the memory goes off in the other dimension. So if you look at the side of the board, it sort of looks like this. There's these boards which have components on both sides, some connectors in between them. These boards which have components on both sides. And then some of the components on these boards are, in fact, SIMs, memory SIMs, so they actually go up like this. So the board is, in fact, a pretty thick 3-dimensional structure. Those boards are the basic replaceable modules. One of the things about making it field repairable is just dumb things like making sure you don't have to pull real hard on the connector in order to get it out, because that'll give you mechanically induced noise in the next cabinet. So there's a lot of mechanics that sort of built-in inserters with levers that sort of very smoothly pull the boards out and things like that. So those boards are packed so that we basically put in a pair of racks, 256 processors. And then there's another rack of communication stuff associated with it. So 3 racks gives you 256. And then those racks are hooked together as big as you need them with the cables running across the top. And it's all air-cooled. Air comes up through the bottom of the floor and blows out through these. In fact, it's very carefully air-cooled so that none of the chip temperatures go above 80 degrees C, which is important to keep the fundamental reliability of the system high. So the packaging is, in some sense, very conservative, but it works out very neatly in terms of its ability to change it sort of live while the system is running. And in fact, I think that maybe I'll stop this part of the talk by showing a picture of it, and maybe I'll get to some of the future stuff in talking about the questions. So let me just show a picture of a 1,000 processor machine. This is one of those 3-rack bays of 256 processors. This is the air plenum going up that you can actually see to the back of the processors. The processors have diagnostic lights on them, which are brought out to this front panel where you can actually read them off. And this would be 1,000 processors in a cabinet. So this would be about 7 feet tall and about 15 feet long, I guess. So that's the basic shape of the machine. So what's important about the machine? I think one of the things that is most important is the programming model. I think that this programming model of having a single program and not having to worry about things like forking and synchronization and so on is absolutely critical. And I believe that any computer that's actually going to do real applications is primarily going to get its parallelism from that model. That's not to say that there won't be occasions where you'll pipeline a few jobs or do multiple instances of programs running at once and so on. I think that will certainly happen, but that's not the primary source of parallelism in parallel computers. The primary source of parallelism is the parallelism across the data. I think the second thing that's interesting is that the SIMD-MIMD debate, I think, is kind of over. As far as I'm concerned, both sides won. If you look at the hardware drawings of this, you say, oh, that's a MIMD machine. If you look at the programmer manual, you say, oh, that's a SIMD machine. And you should be happy either way. And the last comment is I think that because these machines are really scalable, the idea of what's the fastest computer has kind of changed its meaning. Because when you had a computer that could kind of only grow to so big, then it was a real interesting question whether a Cray YMP or a connection machine 2 was faster at this problem or that problem. But this sort of changes the whole notion of a faster computer. We're now to the point where whoever puts the most microprocessors in a box, in some sense, has the fastest computer. And that's uninteresting. What's interesting is, does the computer really have these properties of scalability? Does it really continue to work reliably as it gets big? Can you really run a program on all of it? Can you really program it? Does it have I/O that grows with it? Does the communication really grow? Things like that. So I think that the questions we're going to ask about high-performance computers become a little bit more complicated than just fastest. But I think the answers that we get are good answers. So I'm excited about the prospects of parallel computers. I think these are going to completely replace vector computers very quickly. And I think that the really interesting thing now is sort of what is the influence of these parallel architectures, not just the connection machine architecture, but all the stuff that's going on in massive parallelism, on the programming models, on the programming languages, the types of applications, the types of algorithms that happen. And I think that's really where the action is going to be in computer science over the next few years. So thank you very much. I'll stop there. We did look at fiber optics. In fact, we built a prototype early on of a fiber optic link for the communication system. And we decided that it wasn't conservative enough technology to use yet. So we actually had sort of gigabit fibers. If you use 100 megabit fibers, which are pretty available these days, you're introducing so many new components that you bring the reliability way down. If you use gigabit fibers, it ought to be better, but we were basically afraid to use a new technology that hadn't been field tested a lot. But the way that we've designed the network, you ought to be able to take a bundle of cables, say this bundle of cables, and replace it with a fiber channel. And interestingly enough, that has the potential of helping you not just with the bandwidth, but in a sense it helps you with the latency too, because the latency isn't just coming from the number of hops you're going over, because remember it's pipeline. The latency is also coming from the serialization of this wide message. So going to a fiber channel at some time in the future can help you with both of those. Currently, we are using exactly the same data vaults on the CM5 as on the CM2. We do have some more projects coming up in sort of advanced disk units, which go beyond that. But again, that's sort of a different technology track than the CM5 track. I guess maybe the one difference in the IO architecture, too, is, of course, you have a separate IO control processor, which is orchestrating the interaction. So that's maybe the one difference in how we use it in the CM5. Normally, in a large machine, you would have extra processors which are sitting there waiting for spares. So if you run a 1,000 processor machine, you might have another 32 processors around the spares. So that you would keep the machine the same size and just swap out the bad processors and swap in good processors. Now the way that the data parallel software is written, however, it is possible to take a program that's been running on 1,000 processors and take that image, if you will, and run that same problem on 500 processors. So that's sort of fundamental in the notion of data parallel software is that it doesn't know how many processors it's running on. But in fact, we would normally keep the number of processors the same and just swap in spares. The answer is really no longer than it takes to power up and boot a smaller version of the machine, because it all happens in parallel. So things like loading, the memories are initially loaded through the broadcast network. I mean, I suppose if you're bringing in I/O, typically you have I/O that scales with the size of the machine. So the I/O time of bringing in an initial file image doesn't go up with the size of the machine. I don't know. We have patents on various pieces of it and so on. We weren't aware of anybody who had solved the same problems the same way, but it's very possible that people have. There's two parts to the answer. One of them is that one of the ideas about this machine was basically an idea about how to ride technology curves. So one of the reasons that the massively parallel processors have so far outdistanced the vector processors is because basically we had 100 times as many engineers working on the technology of them than the vector processor people did, that were working on the RISC processors and the CMOS process lines and so on. So the notion was that we had to have a machine where we could take advantage of those improvements as they came along. So one of the ideas was that we very carefully decoupled the design of, for example, the processor chips from the design of the switching circuits in the network, so that we could improve each of those independently and separately. So for example, the way that the clocking is designed, those aren't running off the same clock, they're running off clocks that are phase locked, but they can be different frequencies. So the intent is to increase those processors, but also on kind of an independent technology track, increase the actual clock rates of the memory switches. Now, that will help on bandwidth, but it won't help on latency. And as you pointed out, our best bet for helping on latency is going to be either getting the technology more compact, which means putting more processors on a board, or running more wires. And we left ourselves some room in the packaging and so on to run more wires between the same boards in the future for just that reason.